Good morning, class. All right, so we're continuing along with file system implementation. By the way, who is that creepy guy that keeps saying good morning, good afternoon, good evening? Eeh. So today we're looking at recovery from file system crashes, the network file system, NFS, and the WAFL file system briefly. So one last time, here are the chapter objectives. All right, so with respect to recovery, consistency checking examines the file system's metadata, looking for inconsistencies and tries to fix them. So there's a certain amount of redundancy, for example, within the metadata. Consider a block that's on the free block list, but is also claimed by a file. That's an inconsistency that will either be automatically fixed or will be pointed out to whoever's running the consistency check in Windows, in Windows, and DOS, the traditional consistency check program was checkdisk, is checkdisk. In Linux, it's FISC. These programs tend to need a fair amount of time to run, particularly with today's larger disks, so they aren't run that frequently. By default, for example, Linux requires that FISC be run something like after every 50 mounts, and for particularly large disks, it can take a very long time to run. And as mentioned here, sometimes these consistency check fails, at which point hopefully you have backups of files that are missing or of entire file systems and can restore from those backups. If not, well, you're stuck. So journaling is a technique borrowed from database management systems where it's been used for a fairly long time in order to maintain the integrity of databases, and the information that gets logged to the journal may just be the file system metadata. That appears to be common. Less common would be for the metadata and the actual data in files to be logged. In that latter case, the operation of the journaled file system is slower because you're essentially writing all file system data twice. And the journals, these logs are designed in such a way that if a file system crashes, either all the metadata for a file has been updated or in the actual file system, or none of it has. So the metadata is kept in a consistent state, which speeds recovery. Of course, if the journal isn't logging file blocks themselves, then a particular file might be in an inconsistent state. But in some sense, that's better than leaving the entire file system in an inconsistent state. So NFS was created by Sun, but it is used extensively in Linux and in most, if not all, of the various flavors of Unix. I'll just point out here that even though this is being advertised as an unreliable protocol, typically UDP is only used on LANs where one doesn't have to worry about packets being dropped or duplicated or anything like that. NFS will also run on TCP, which is reliable and would probably be the protocol of choice if one were running NFS across a WAN, which for security and other reasons probably wouldn't be a great idea. So NFS's mount semantics are similar to what we saw earlier with mounting a local file system within a file system tree in that an NFS mount is mounted over a node in a local file system, that node being a directory, and that's transparent to users. As noted here, the mount itself is non-transparent in that the NFS server needs to be named. So NFS is a standard, which means it works across various operating system platforms and across different hardware architectures, which is where something like the external data representation protocol will come into effect, because a client might be running on a CPU that's little endian, whereas the server might be running on a CPU that's big endian, which of course means that the bytes within a data word will have to be reordered as they're passed from client to server. And as mentioned in the third bullet, an NFS implementation runs a mount daemon on the server, which handles mount requests, then the NFS daemon that handles the actual file system operations, and finally, separately, because this is not specified as part of the NFS protocol, a lock daemon to handle file locking. So in this example, we're going to see we have a client and two servers. The end result will be shown on the next transparency. This mount point will be first mounted here, meaning that these files are available in /user/local on the client, and then in a cascading mount, this directory is going to be mounted here, which means by the client, not by this server. So on the client, then files here will be available in user local dir1. Right. So here are the directories from the first server, and then here's this shows the cascading mount as mounted by the client. So here we see that NFS is built on top of the remote procedure call protocol that we studied a while back. Servers maintain export lists, so that specifies names of clients that are permitted to mount certain named directories, as well as the options for mounting those directories, such as whether, for example, requests from root on the client will be squashed to a non-root user, whether the client's allowed to mount the server's directory read-write or just read-only, for example. I'll mention in passing that this mechanism of this boils down to security by IP address, which isn't particularly secure. That's one reason why one wouldn't want to open an NFS server across a wide area network. And actually, it's not that secure across a local area network either. All right, so here with respect to NFS operations, we have many typical file system operations here, but note that open file and close file, there's nothing corresponding to those system calls here, and that's a result of NFS being stateless. Maintaining file handles from open files will be maintaining state, and the problem with maintaining state occurs when an NFS server crashes. If it comes back up, then it's lost that state, and then clients are in the clients and the server then are in a very inconsistent state. So part of stateless means that data has to be committed to the server's disk once data is flushed from the client to the server. Of course, there wouldn't particularly be anything requiring a client to immediately flush write data to the server. It could be cached there, but once the client does flush it, that RPC won't return until the data has been written. And as I mentioned earlier, there's a lock daemon that runs outside of the NFS protocol to handle concurrency control. Okay, of course, to a user program, the user program is still going to open and close files using file descriptors, but that's a layer of abstraction, and when you think about it, that's not something that we would want to change for processes that are working with files that are served across NFS. That's then the layer below that is a virtual file system, which is an abstraction layer built upon all the file systems that an operating system provides. So, for example, for Linux, that could be Rockridge for optical drives, ext3 or ext4 for traditional disk drives, and now NFS. And then, of course, below the virtual file system layer, we have the NFS service layer. So here we see a traditional layered architecture. Here are the client and server applications that interface to the kernel through system calls. The VFS abstraction interface to NFS client, to RPC, XDR, then the layers of a networking protocol, and then up the stack through NFS on the server and down through the traditional Unix file system. So all this is really telling us is that path name traversals, where one is hunting through several layers of directory, is an expensive operation because each path name component is going to result in its own set of RPCs and IOs. So not surprisingly, the translations can be cached on the client side so that the entire path doesn't have to be traversed every single time a file is referenced. Right? And because of the stateless nature of NFS, the path names would have to be traversed on every single read of a data block or write of a data block, right? Because the client doesn't have, otherwise wouldn't have handles, a file handle to the file. All right, I don't see anything to add to this, so I'm going to skip this slide. The one thing that I'm going to point out about WAFL is its snapshot mechanism, which isn't mentioned here, so I'm going to skip this slide. So at an instant in time, this is what the state of the WAFL file system looks like. So when a snapshot is taken, metadata is copied. Note that the blocks themselves are not copied unless a block changes, in which case the original of the data is still available. Sorry, I got lost there for a second. The original of the data is part of the snapshot. The updated data, of course, is with the current state of WAFL. So this is a fairly efficient way of keeping backups, for example, or of course, snapshots can be used to take the file system back to a particular point in time and make available multiple copies of files within the file system, right? Those copy is kept each time a snapshot is taken. All right, so that finishes chapter 12.